I welcome you all to my 40th lecture on digital signal processing, that is UEC 502 for electronics and communication engineering students and electronics and computer engineering students. Today we will discuss adaptive linear equalizers. In the case of linear equalizer, we have considered two different criteria for determining the values of equalizer coefficients Ck. One criterion is based on the minimization of the peak distortion at the output of the equalizer, which is defined as d bracket c is equal to summation n running from minus infinity to infinity when n is not equal to 0, magnitude summation j running from minus infinity to infinity cj f cap n minus j. And this is further equal to summation n running from minus infinity to infinity when n not equal to 0, magnitude qn. Mark it as equation A, which we have discussed previously. The other criterion is based on the minimization of mean squared error at the output of equalizer, which is defined as J is equal to expectation bracket magnitude EK square, and which is further equal to J is equal to expectation bracket magnitude IK minus I cap K square. Mark it as equation B, which has been discussed earlier. Based on these above mentioned criteria, we describe two algorithms for performing the optimization automatically and adaptively. So first we will discuss the zero forcing algorithm based adaptive equalization. In the peak distortion criterion, the peak distortion mentioned in equation A is minimized by selecting the equalizer coefficient Ck. For finite length equalizers, d bracket c is equal to summation n running from minus m to m plus l minus 1 when n is not equal to 0, magnitude qn, and which is further equal to summation n running from minus m to m plus l minus 1 when n is not equal to 0, magnitude summation j cj f cap n minus j. Mark it as equation C. For one typical case in which the distortion at the input to equalizer d naught is less than unity, the solution for the minimization of DC is known, where D naught is equal to 1 by magnitude F naught cap into summation n running from 1 to L, magnitude F cap n, marked as equation D. This condition is equivalent to having I open prior to the equalization. Under this condition, the peak distortion DC is minimized by selecting the equalizer coefficients to force Qn is equal to 0 for magnitude n lying in the range 1 to m and Q naught is equal to 1. Therefore, the general solution to minimization of DC when D naught is less than 1 is the zero forcing solution for Qn in the range magnitude n lying in the range 1 to m. However, non-zero values of Qn for n in the range m plus 1 to m plus l minus 1 constitute the residual ISI at the output of the equalizer. So the non-zero values of Qn for n ranging from m plus 1 to m plus l minus 1 constitute the residual ISI at the output of the equalizer. The zero forcing solution is achieved by forcing cross correlation between the error sequence Ek, that is equal to Ik minus I cap k, and the desired information sequence Ik to be 0 for shifts in the range magnitude n lying in the range 0 to m, such that expectation Ek I conjugate k minus j is equal to expectation bracket Ik minus I cap k into I conjugate k minus j. Mark it as equation G, which is further equal to expectation bracket Ik I conjugate k minus j minus expectation bracket I cap k into I conjugate k minus j. Mark it as equation K. Now we assume that the information symbols are uncorrelated. That is expectation Ik into I conjugate j is equal to delta kj, and that the information sequence Ik is uncorrelated with the additive noise sequence eta k. But we know that the output of equalizer at kth sampling instant can be expressed as I cap k is equal to summation j qj I k minus j plus summation j cj eta k minus j. Mark it as equation n. Using equations k and n, look at this. I want value for this. So using equation k and n, it can be shown that expectation bracket ek into I conjugate k minus j is delta j0 minus qj for j in the range minus m to m. Mark it as equation O. Therefore, the conditions expectation bracket ek I conjugate k minus j is equal to 0 for j lying in the range minus m to m are fulfilled when q0 is equal to 1 and qn is equal to 0 for magnitude n lying in the range 1 to m. Mark it as equation P. Now, this is very important. When the channel response is unknown, this is very important. When the channel response is unknown, the cross correlations given by equation G are also unknown. So look at equation G. So the cross correlation, the cross correlation given by equation G are unknown. This difficulty can be circumvented by transmitting a known training sequence IK to the receiver, which can be used to estimate the cross correlation by substituting time averages for the ensembled averages in equation K. So in this equation, we will use time averages. After the initial training, which will require the transmission of a training sequence of some predetermined length that equals or exceeds the equalizer length, the equalizer coefficients that satisfy equation P can be determined. A simple recursive algorithm for equalizer coefficients is Cj with superscript k plus 1 is equal to Cj with superscript k plus delta into Ek I conjugate k minus j for j ranging in minus m to m. Mark it equation R, where Cj with superscript k is the jth coefficient at time t is equal to k capital T, and Ek is equal to Ik minus I cap k is the error signal at the time t is equal to k capital T. And delta is the scale factor that controls the rate of adjustment. This is the zero forcing algorithm. So this is the zero forcing algorithm. Now the term Ek into I conjugate k minus j is an estimate of cross correlation, that ensembled average, that is expectation bracket Ek I conjugate k minus j. The averaging operation of cross correlation is accomplished by means of the recursive first order difference algorithm in equation R. Following the training period, when training is over, after which the equalizer coefficients have converged to their optimum values, the decisions at the output of detector are generally sufficiently reliable so that they may be used to continue the coefficient adaptation process. This is called a decision-directed mode of adaptation. In such a case, the cross correlation in equation R, look at equation R, the cross correlation, in this case, the cross correlations in equation R involve the error signal E bar k is equal to I bar k minus I cap k, and the detected output sequence I bar k minus j for j ranging in minus m to m. Thus, in the adaptation mode, or thus in the adaptive mode, the equation R becomes Cj with superscript k plus 1 is equal to Cj with superscript k plus delta into E bar k I bar conjugate k minus j. Mark it as equation S. Now this is in the decision directed mode when we are using decisions for updating the tap coefficients. The following figure illustrates the zero forcing equalizer in the training mode and in adaptive mode, that is decision directed mode of operation. Now look at this. Input is Pk, which is unequalized and given to the equalizer. This is delay element, this is multiplier, and this is detector. So this the output of this transversal filter where the tab coefficient are Cj with superscript k, which need to be updated. We have output at this transversal filter as I cap k, and from by using detector, I can guess the signal I bar k. So this is the detected symbol. Now this is training sequence generator and output is Ik. When this switch is connected to this, then Ik will flow inside. So here Ik minus I cap k will give Ek, which is further utilized here and multiplied by delta and supplied here to update the coefficient Cj with superscript k. Now this is the diagram of an adaptive zero forcing equalizer. And when training period is over, this switch moves to this place. And now the output of detector, that is I bar k, will be utilized further in the adaptive mode. So here Ek will here there will be E bar k is equal to I bar k minus I cap k, which is multiplied by delta. So equation S, this is in the adaptive mode. So this is the block diagram, or this is the diagram for an adaptive zero forcing equalizer. Now, the linear adaptive equalizer based on MMSE criteria. In the minimization of MSE, as discussed earlier, the optimum equalizer coefficients are determined from the solution of the set of linear equations expressed in matrix form as tau vector into C vector is equal to xi vector. Mark it as equation T, where tau vector is the 2m plus 1 into 2m plus 1 covariance matrix of the signal samples. Here, tau vector is the 2m plus 1 into 2m plus 1 covariance matrix of the signal samples pk. C vector is the column vector of 2m plus 1 equalizer coefficients, and xi vector is a 2m plus 1 dimensional column vector of channel filter coefficients. The solution of the optimum equalizer coefficient vector C optimum can be determined by inverting the covariance matrix tau vector. This we have done in the previous lecture. The direct matrix inversion can be avoided while computing C vector optimum by using the method of steepest descent and iterative procedure. Here, the succeeding values of the coefficient vector C vector are obtained according to the relation C vector k plus 1 is equal to C vector k plus delta into G vector k, where k is changing from 0, 1, 2, and so on, mark it as equation U1. The vector C vector k represents the set of coefficients at the kth iteration, and G vector k is equal to 1 by 2 d by dc vector k of j is equal to tau vector into C vector k minus xi vector, and that is equal to minus expectation bracket ek p vector conjugate k, mark it as equation U2, where ek is equal to ik minus I cap k is the error signal at the kth iteration, and p vector k is the vector of received signal samples at the here the p vector k is the vector of received signal samples that make up the estimate I cap k. That is, p vector k is equal to bracket pk plus m to pk minus m transpose. And delta is the positive number chosen small enough to ensure convergence of the iterative procedure. In the iterative procedure, one begins by arbitrarily choosing the vector C vector is equal to C naught vector. This initial choice of coefficients corresponds to some point in the quadratic MSE surface in the 2m+1 dimensional space of coefficients. The gradient vector G vector naught having 2m+1 gradient components 1 by 2 J partial differentiation of J with respect to C naught K when K is changing from -m to m is then computed at this point on the MSE surface. And each tab weight is changed in the direction opposite to its gradient component. The change in the jth tab weight coefficient is proportional to the size of the jth gradient component. If the minimum MSE is reached for some k is equal to k naught, then gk is equal to 0, so that no further change occurs in the tab weights. In general, J minimum M cannot be attained for a finite value of K naught with steepest descent algorithm. However, it can be approached as closely as desired for some finite value of K naught. This basic difficulty with the method of steepest descent for determining the optimum weight vector is the lack of knowledge of the gradient vector G vector K in equation U1 due to unknown channel statistics and parameters. To overcome the difficulty, the estimates of the gradient vector may be used. Now, the algorithm for adjusting the tab weight coefficients may be expressed in the form C cap k plus 1 is equal to C cap k plus delta G cap k, marked as V1, where G cap k denotes the estimate of gradient vector G vector k, and C cap k indicates the estimate of vector of coefficient C vector k. The estimate of G vector k based on equation U2 can be expressed as G vector k is equal to minus EK P vector conjugate k, marked as V2. Since expectation bracket G cap k is equal to G vector k, therefore G cap k is an unbiased estimate of the true gradient vector G vector k. Consequently, the algorithm for adjusting tab weight coefficients is C cap k plus 1 is equal to C cap k plus delta into EK P vector conjugate k, marked as equation V3. This is the basic LMS least mean square algorithm for recursively adjusting the tab weight coefficients of equalizer. Now, the linear adaptive equalizer based on MSE criterion is illustrated below. Now, here at input, we have PK, which is unequalized, and this Z inverse indicates a delay element. This is multiplier, and here these are the coefficients C0, C1 to Cm, starting from C minus M. Now, the output of this transversal filter is I cap K, and here it is detector, which gives us output, the detected symbol I bar K. Now, as discussed earlier, this is the training sequence generator, and when the switch is here, it will give IK. And now here I have EK is equal to IK minus I cap K, and which is multiplied by delta and fed to this. Now, in the decision directed mode, this switch will move here, and now E bar K will be equal to I bar K minus I cap K, which is multiplied by delta and fed for weight updation using this equation V3. So this is the linear adaptive equalizer based on MSE criterion. It will work in two modes, training mode and other is decision directed mode or adaptive mode. In the training mode, we will use known symbols IK, and in the decision directed mode, we will use the output of detector to update these tab coefficients. So here I finish this article. For journal FIR-Filters, you can consult the book of John G. Brockes on digital signal processing. But this lecture is from the reference book by John G. Brockes on digital communications. So the students interested in studying this article in detail, they can consult this book, that is Digital Communications by John G. Brockes. So thanks for attending this session on DSP. See you in next lecture.